I'd now like to talk about the other method of estimation that I promised this week. And so that other method is called maximum likelihood estimation. I'd like to start by just giving you a little bit of history on this. This method was first proposed by Ronald Fisher in the 1920s. So method of moments was Carl Pearson's method from the 1890s. Fast forward about 30 years and Ronald Fisher proposed this. Fisher's another name that you should know. So he's perhaps the most famous statistician of the 20th century. He is really one of the fathers of modern statistics. The F statistic that you've probably seen before is named after Fisher, and many other techniques are his his product. So let's start out with a problem. So the problem I'm going to consider is as follows. Let's say that I have some coin and I don't really know what the probability of a head is. So let us say that P is equal to the probability of a head. And so I'd like to find out what the probability of a head is. This coin, maybe it's it feels kind of unbalanced to me. So I don't think it's a fair coin. So I'd like to test this out. And so here's what I do. I go flip the coin and I get the following sequence. I get head, tail, tail, head, head. And so the question I have for you is, what is your best estimator of the probability of a head? Now, of course, in real life, I wouldn't just stop with 5 flips. Maybe I would do it 1,000 times to make my estimate a little bit more reliable. But we can see the point if we just do 5 flips. So the idea of maximum likelihood is simply this. We're going to write out the probability of observing this. So what is the probability? Let's say that x sub I is equal to 1 if flip I is a head, 0 if it's tails. All right, so what is the probability that x1 is equal to 1 and x2 is equal to 0? I gotta get my subscripts right here, and x3 is equal to 0, so that's a tail, and x4 is equal to 1, and x5 is equal to 1. Well, maximum likelihood says I want to choose P, so choose P to make this probability as large as possible. So pick my P to make that expression as large as possible. So let's go back to the course packet for a second, and I'm going to just give you some general advice on this. So let's say that we have some random variable with a distribution f and some set of parameters. We usually call these parameters theta in general. So theta could be a vector. It could just be a single parameter, as is my example of a coin flip. Now, I observe n IID observations, so they're independent and identically distributed. So what this means is with my coin flip example, I'm going to flip the same coin each time. So that makes them come from the same identical distribution, and one coin flip doesn't affect another, meaning they're independent of one another. And so I've recorded their values, x1 through xn. So the maximum likelihood estimator defines the likelihood, which, since my observations are independent, this likelihood is just going to be the product of each of my individual cases. Now, in the case of a discrete distribution, this distribution is just going to be the product from I equals 1 to 5, the probability of x sub I equaling whatever the value I've observed, little x sub I. So if you want to write this all out, it's the probability that x1 equals 1 times the probability that x2 equals 0 times ... times the probability that x5 equals 1. Let's write that as neatly as I can at the end of the page here. All right, so we're just going to compute the product there. We're going to call that the likelihood. And then, as I described earlier, the maximum likelihood estimator is the value theta hat that maximizes the likelihood function. Now, in the case of numerical random variables, you're going to have PDFs rather than PMFs, and you don't really interpret that as a probability. We still multiply the PDFs as I multiplied the PMFs in the case of my Bernoulli trials. Now, in general, this is a difficult expression to deal with. So as soon as you see the word maximize, you should start thinking about having to take the derivative of this. We'll set the derivatives to 0 and solve for that. But there's a big product here. And so taking the derivatives of products is difficult, right? You have to use the product rule, and that gets messy. So I'd really like to avoid having to take the derivative of a big product, in this case involving n terms. So the way we can avoid this is take a monotonic transformation of both sides. So the monotonic transformation is the log, and when we do that, we don't change the location of the maximum, but we make it much easier to take derivatives. So if I take the derivative of both sides, that product becomes a sum, and sums are easy to take derivatives of. One more thing, the notation that I like to use for the likelihood is big L evaluated at my set of parameters. The notation that I use for the log likelihood is to use a little l evaluated at the parameters. Now, before we get into some examples, we need some examples. I'm just going to mention that under very general conditions, these maximum likelihood estimators have very desirable properties. So they're approximately unbiased. They are approximately minimum variance, so MVUE. So they have the smallest variance among all unbiased estimators. Turns out they're also approximately normal, which means that we're going to be able to use the normal distribution for finding confidence intervals and doing hypothesis tests on these MLEs in the chapters that we'll study next. And so these MLEs have just many very desirable properties, and that's why this is one of the preferred methods of estimation. So at this point, let's go back to my my example over here, and let's think of this as a binomial. Okay, so if we think of this as a binomial, so we're going to account for all the different orderings, not that that really matters that much. My likelihood function is going to be this. I'm going to have 5 flips, and I've observed 3 heads. Then P is the probability of a head, and I need 3 of those. 1 minus P is the probability of a tail, and I need 5 minus 3, or 2 of those. So I had 2 tails, I had 3 heads, and this would be my likelihood. The log likelihood, so L at theta, is just going to be the log of L at theta. which is equal to 5 choose 3, by the way, is 10. So this is going to be the log of 10. Now, this product is going to work out as follows. That product becomes a sum. So this is going to be 3 copies of the log of p. And then I have 2 copies of the log of 1 minus p. And so there's my log likelihood. So remember, the maximum likelihood expression is going to be find the value of p that makes this expression, or equivalently this expression, as large as possible. So let's go do that. I'm going to find the derivative of L at theta with respect to theta. Maybe I should be calling this p rather than theta. Theta, remember, is just my general expression for a parameter. P is the specific parameter in this case of a bunch of coin flips. So let's go find the derivative of this. What's the derivative of the log of 10? Well, that's just a 0. So that's why I said it doesn't really matter whether we account for the ordering or not. It would just shift the likelihood up or down. When I take the derivative, it has no effect. So that 0 is there. All right. Let's go take the derivative of 3 log p. So that's going to be 3. What is the derivative of log p? Well, the derivative of the log is 1 over p times the derivative of p, which is 1. So we're using the chain rule there. So the derivative of this term is just 3 over p. And let's go do the last term. So this is going to be plus, well, this is going to be 2. What's the derivative of the log of 1 minus p? Well, it's going to be 1 over 1 minus p. Then using the chain rule, what's the derivative of 1 minus p? It's a minus 1. So minus 1, we'll just put a minus sign in front. So all of this has to equal 0. So let's go, I'm going to move this term to the other side. 3 over p is equal to 2 over 1 minus p. And I can multiply both sides by p times 1 minus p. So p times 1 minus p. And if I do that, that p crosses out, the 1 minus p crosses out. So I'm left with 3 minus 3p is equal to 2p. And I'll move this to the other side. So 5p is equal to 3. P is equal to 3/5. Or we could stick a hat on that if we like. That is our maximum likelihood estimator of the binomial or Bernoulli trial. So I guess I've defined this as a Bernoulli trial. If you account for the order, the different orderings, then it'd be binomial. Doesn't matter. In both cases, it's count the number of heads and divide by the number of flips. And that's your maximum likelihood estimator. So that was a fair amount of work for something that that is probably fairly obvious. That would be the obvious thing. But now we have a solid rationale with a lot of very desirable properties. Let me give you a couple more examples. So the next example that I want to give is that of a normal distribution with a known variance. So let's say that x is normal with known sigma squared. So let's now write out our PDF. So the PDF is this: x given the parameter, unknown parameter mu, and sigma squared is known at this case. So what is the PDF of a normal? Well, it's 1 over the square root of 2 pi sigma squared. Make sure that square root covers everything. Then I have e to the negative 1 over 2 sigma squared x minus the mean squared. Now, let's say I have x1 through xn as an IID sample from this distribution. So we've identified our PDF. Let's go write out the likelihood. So the likelihood in this case is going to be L at mu, and this is just going to be the product from I equals 1 to n of these individual PDFs. So I guess I'll copy it again. So 2 pi sigma squared is what sits down here. E to the negative 1 over 2 sigma squared xi now. So that's the only difference here is I have to keep track of my subscript minus mu squared. Well, I want to find the value of mu that makes this expression as large as possible. That would be fairly difficult because I have a product. So in order to avoid that, let's go take the log of both sides. So let's write this as little l at mu, which again is the log of L at mu. And this expression is equal to, when I take the log of a sum, the log of a product, this becomes a sum. So I equals 1 to n. And let's see what we have here. I've got the log of this constant, 1 over 2 pi sigma squared. There's really a square root there. And then I have a product, so this constant times this thing, so there's a times sign in there. That times sign becomes a plus. So we can think about plus the log of this. Well, what's the log of e to the something? It's just, the log of the exponent, since they're inverse functions, it's just this quantity up here. So this is going to be minus 1 over 2 sigma squared xi minus mu squared. All right, we're actually making a lot of progress here. So I want to take the derivative of this, so dl at mu, d mu. So what is the derivative of this first term? Well, notice this first term does not involve mu. Therefore, the derivative of that first term is just a bunch of zeros, just a 0. So we can think of this as 0. And then let's go find the derivative of the second term. So it's going to be 1 over 2 sigma squared. That's a constant. Then I need to use my chain rule here. We're going to bring the exponent down, so 2 times the base, so xi minus mu, raised to the, 1 power. And then I have to take the derivative of the base. So the derivative of the base with respect to mu is just minus 1. So we can think of this as times minus 1. So I'm just going to make that minus a plus. My 2's cross out, and that's my expression. So that's a sigma squared. All right, all of this has to equal 0. So let's go solve this. What we have is, well, I'll write it like this: 1 over sigma squared times the sum of xi minus, what do we have here? I've got the sum of n of those mu's. So that mu doesn't have a subscript. This is ranging from I equals 1 to n, so I'm just adding up n mu's here. That has to equal 0. So I can multiply both sides by sigma squared to get rid of that. And so this whole thing is still 0, of course. And where I'm going with this is we end up with the sum of xi is equal to n mu. Therefore, mu is just 1 over n times the sum of xi, and we recognize that as x bar. So it was a lot of work, a lot of math to come up with. This was also the method of moments estimator. So that's the estimator of the mean. There's a fairly more complicated situation where sigma squared is not known. And if sigma squared is not known, then you're going to have a system of two equations in two unknowns, and you'll have to solve that. And the algebra becomes a little bit messy. I'm not going to do it for you. I believe it's in the textbook. So I'll give you one more example, and that example is an exponential distribution. So let's say that I have x1 through xn as an IID sample from the following PDF. So f at x given lambda is just lambda times e to the negative lambda x. And so the question is, what is the maximum likelihood estimator of the exponential distribution? So this is exponential. So the procedure is the same as before. Let's go write out our likelihood. So the likelihood is going to be the product from I equals 1 to n of the individual PDFs. So lambda times e to the negative lambda x sub I. So the only difference, as we had with the normal, is I put a subscript I there. Well, let's go write out our log likelihood. So remember, I want to make this as large as possible, so I want to maximize it. How do I do that? Well, I don't want to take derivatives of a bunch of products, so we're going to take logs of both sides. So take the logarithm of L at lambda. And this is equal to the sum, I equals 1 to n, and I have the log of lambda, so that's that first term, plus the log of the second term. So notice I have the log of e to something, so that's just whatever that exponent is. So this is going to be minus lambda xi. All right, so let's go take our derivative. So I want to make this as large as possible. So dl at lambda is the following. So what is the derivative of the log of lambda? Well, this is all inside my sum, I equals 1 to n, of 1 over lambda times the derivative of lambda, which is 1. And then what's the derivative of negative lambda xi? Well, this is just minus xi. So we're going to set this equal to 0. And let's go see what we end up with. So I have n copies of 1 over lambda. So let's just write that as n copies of 1 over lambda. So n over lambda. And then what do I have here? I have the sum of my xi's, and that all has to equal 0. So n over lambda has to equal the sum of my xi's. Therefore, lambda is equal to n over the sum of xi's. But notice this is equal to really 1 over x bar. So what's x bar? X bar is 1 over n sum xi's. 1 over x bar then would of course be this expression. So it's just 1 over the sample mean. And if we go back to my course packet for a second, earlier we did the method of moments estimator and found exactly the same quantity. Let me mention a couple things. Number one, the method of moments estimator does not always equal the maximum likelihood estimator. Sometimes they are different. Number two, I was slightly sloppy in that I didn't evaluate the second derivatives. So we should probably compute the second derivatives for each of the examples I just did and make sure that the second derivative indicates that we have a maximum. So that second derivative ought to be negative. I did not check that, but that's something you should do. All right, that's it for my, my introduction to maximum likelihood estimation.